So I'm Adeeb. I work on openpilot, and I'm going to talk about mostly testing, but as Alex said, there's going to be a couple of fun announcements at the end. So we're going to talk about quality and how we don't break stuff, because openpilot's getting to be a big project, and we support 2 hardware platforms now with 2 different operating systems, one based on Android and one based on Ubuntu. We do roughly monthly releases that are fairly large. This one in particular was a recent one that was pretty large. This one. So these are a couple of releases that we did recently. They're pretty big. We have a small team. We support 132 cars as of today, various brands. And we have over 200 plus contributors in the since last January, since we changed the development style, and we develop publicly now. So how do we not break stuff? This is a commit from 2016, and we had a dream back then. One day we'll have CI. And then here we are, July 2021. So these are some randomly sampled desks at the office, and you'll notice there are no common devices on these desks. They're just computers. They're Ubuntu workstations. And this is largely our development workflow now. We sit at desks, not in cars anymore. And the answer to how we don't break stuff is we have automated regression testing and unit testing. We do hardware in the loop tests. We do offline checks for anomaly detection, and we do online checks on the device. So the testing goals for openpilot are enforcing quality, reducing the time spent in cars, as we showed with that picture on the desks, and efficiently scaling a small team. Because the openpilot team is about 3 full-time people with a research team that is now 4 full-time people. And we have a very concrete goal of 1,000 hours mean time between failure for 1.0. So some of the automated checks we do, these are the public ones at least. We have a GitHub Actions test suite that runs unit tests, this test process replay that's fairly important, and we do these car unit tests that are also pretty important. Then we have a Jenkins server that runs our hardware in the loop tests, where we have comma 3s and comma 2s, going on road, running real segments, doing replays, and enforcing things like, are the timings as good as we want? Is the CPU usage exactly as we expect it to be? Things like that. And then you guys have probably seen the online checks if you've used openpilot. Sometimes you'll get a fan malfunction. Sometimes you get a GPS malfunction. It'll say contact support, and then what do people do? They go to Discord. But when the alert works, you should contact support. And we try really hard to make these alerts and be very aggressive about it, but also prevent the stuff from going out in the field. But yeah, we do some pretty extensive checking across all the different services in openpilot. We make sure that all the services are live, they're healthy, and their sources for data are also healthy. So if like one of the sensors is bad, for example, this will propagate all the way through location D, through the planner, and controls will say, okay, we can't engage now, or we have to disengage now. And then this is one of our more important tests that runs in GitHub Actions. It's called process replay. And we can deterministically replay segments through routes, or through processes. And we can take the same set of inputs and assure that we get the same set of outputs. And if we don't, we generate these nice diffs, as you can see here. So this is a diff for for actually the new model that we just tried to ship in 087, but we had to revert, which will hopefully ship soon. But this is the diff that it generated. We switched to some different lead packets and stuff. So you'll notice the difference here. It tells you exactly what changed. And we can know, given 2 different commits, what will the outputs of this particular openpilot service be? Did they change in the ways that we expected, or did they not change? So a lot of times we'll do a refactor where we expect that nothing changes. And this is pretty important because we can do things like we can review PRs really quickly. You read the diff, you make sure the diff is reasonable, you do your diligence there. But if the green check mark is there on GitHub Actions, you can be reasonably certain that this did not change any behavior of the tested openpilot processes. And this runs on all the driving processes. So there's 6 critical driving processes, and this covers all of them, and some other ones. Then we do some car unit tests. And these car tests are super important for scaling to these 132 cars that we haven't really touched. So we have 6 cars at the office right now. We've probably touched somewhere in the neighborhood of a few dozen cars over the lifetime of the company. But all the other ones come through pull requests. Pull requests that are fairly small, but it's still important to make sure that these cars work because we sell devices, we want to ensure quality, and there's really no reason not to. We invested quite a bit of time in making these very reliable unit tests, and now we can be reasonably certain that every car that openpilot has a test route for functions to some degree. We don't necessarily check driving behavior, but we check system behavior. Will this car throw a CAN error? Will the frequency checks work on this car? Will Panda safety agree with openpilot? Because if this isn't true, as you heard in Robostock, the Panda will just block the messages. So this asserts some very basic behavior and allows us to effortlessly scale to the next milestone in cars, which maybe is 250, 1,000 cars. And then this is part of our suite of offline anomaly detection. So we have a pipeline stage called Find Interesting that runs on all the incoming data. And this runs on those Q logs that anybody who runs openpilot uploads. And these are some tiny logs that we get a lot of information about all the devices in the field. So this is like a real screenshot from our dashboards that we have up in the middle of the office. So you can see right now, some of the top errors are with, there's some Panda stuff, there's some Camera D stuff on the Comma 2, there's a little bit of poor model timings on release, and we have this cool iteration loop we do with Find Interesting where we aggressively log everything that we expect to happen with openpilot, and then we look at it and Find Interesting, and we look at the data that comes in, and if this isn't happening, it's going to show up and Find Interesting, and it's going to be one of these top things. Oops. Clickers are hard. Oh, yeah, there we go. So you see that these Panda errors are dominating right now. A year ago, it used to be overheats, CAN errors, all these other things. But every release, we look at the top few things, and we fix them. And then you just end up with a way more reliable system when you're tracking the things that you care about. Because if we don't track these things, they're going to regress. And this is our testing closet. You may have heard about it. It's a little bit of a strange name, but the name comes from the closet it was originally housed in the original comma house. And you can see some comma 3s here running different branches. You can see some comma 2s. These comma 2s are running a NeoS update that was supposed to ship in a previous release, but that didn't make the cut because of some things we found in Find Interesting that I'll show you in the next slide. But this is how we verify something like the long tail reliability in that there's no reason openpilot shouldn't just run if we connect it to what we call a jungle. And this allows us to essentially emulate the behavior of being in a car and driving around. There's no reason it shouldn't run for days and weeks and months. And these comma 2s here have been running for a little over 4 weeks so far. This was with, obviously, a version of openpilot from about a month ago. But we update these devices fairly often, and we're able to be reasonably confident about the reliability and behavior of these devices and openpilot because of the data we get back from the testing closet. Here's some plots from the testing closet. These are diffs of consecutive messages from different openpilot servers. So we have calibration D's message, we have one from demodeling model D, we have one from the planner, and we have one from demodeling model D. So these are 4 different openpilot processes that we're looking at messages from. And we can see that the timings are, they're pretty good for the planner. They're a little bit worse for demonitoring model D. And then you'll see demonitoring D and demonitoring model D follow because they're driven by each other. But we can assert some timings, as we can see in the next slide. So this is the timings of board D. So board D is a process that talks to the panda in your car. So that's, you have, if you remember from Roby's talk, you have your comma device, the comma 2 or 3 now, and you have the panda, which is built into the device, but nevertheless, it's a distinct device. And we talk to it over USB on both devices right now. And this timing is super important because it drives the rest of the stack. The camera and the panda drive the stack, essentially. And that's why camera D and board D are super important for latency and real-time performance. So if board D is performing poorly, the rest of the processes that rely on board D are going to perform poorly, such as controls D, which is what actually talks to your car. So we worked really hard to get these timings to the point where it doesn't miss a cycle anymore. And then this is why we didn't ship that NeoS update a couple releases ago. There's still a PR open for NeoS 18. About a year ago, we wrote this daemon that fixes these random can errors where you would get lags on comma 2s randomly, where it would seem that board D just wouldn't run for dozens of milliseconds, and then you get these lags because of our strict online checks. So you can see out in the long tail here, you have it lagging for almost 100 milliseconds. And it does this quite a few times. If we go back to the previous slide, it never does this. So this is some of the behavior we assert in the testing closet. So it's pretty important for assuring that we don't ship regressions and that we're hitting the targets that we aim to. And this is pretty cool. So all of the GitHub action tests that we run on our repo, you can run on your repo too. We've put the effort in to the point where you can click the fork button, and then you click allow actions, and you will have a large portion of our testing infrastructure running on your fork. There's many popular fork maintainers out there who have sometimes hundreds of users. And you have all this testing infrastructure that we've built up. You can, if you support cars that we're never going to support, for example, the Mazdas that have the steering lockout, we don't intend to support these cars, or at least claim that they're an open pilot experience. But you can reach as much as you can. Like you can support the car to almost the full extent that we can by using the test infrastructure that we have. And it's really, you click this one button, you go into the settings for your forked repo, and you enable GitHub Actions. Now we're going to talk about Panda testing. So we have 2 goals for Panda. It should enforce the functional safety that we've defined for openpilot, and it should enforce the hardware functionality. So, you tell the Panda to send this CAN message, it just sent the CAN message. So here's an overview of the testing infrastructure for Panda. We do unit tests, again, in GitHub Actions. We do replay tests, where we take a segment, and it's very similar to process replay, where we assert that the behavior hasn't changed from commit to commit. And then we do some static analysis. Roba talked a little bit about MISRA, I think, in his Q&A, and ISO 262. So our unit tests and our static analysis go a long way to cover the code rigor that we uphold in Panda. That isn't necessarily a goal of openpilot. And then we have hardware in the loop tests that run on the whole zoo. So they run on every Panda that we've ever made, from white, gray, black, uno, dos. So our safety unit tests are pretty cool because you can write all the functional safety you need for a brand new carport, and you can write a test for it. And on average, the test is about 165 lines, which is something you can reasonably do in an afternoon or a weekend. And you can develop functional safety for your brand new carport and verify functionality without ever going in a car or even doing a replay. So I think this is incredibly cool. And we have tests for all these cars, all these safety modes that ship an openpilot release. And this runs for every hardware combination of every car we support. So we support 132 cars. We support quite a few pandas. That's a lot of combinations. And then we do hardware in the loop tests. We assert things like can latency, can loopback. This essentially maintains that if I send out a message, do I get it back? And we can do this with multiple pandas. We use something I'll talk about a little bit later, the panda jungle. We also do some checks with the car harness that we're correctly detecting ignition, all this other kind of stuff. And then I want to talk a little bit about production, building devices, because this is also pretty cool. George talked a little bit about screen calibration. This is some of the stuff we've just gotten to do because we've gotten really good at testing these devices that we can do the fun stuff. We'll go back. So after your common device is built, what happens? So we flash it with NeoS or Agnos, depending on whether you have a common 2 or 3. We do some initial checks to filter out defective units. And then we have this provisioning stage, which runs quite a few tests and asserts all the hardware functionality that we design our common devices for. And then we have a 24-hour stress test that George talked a little bit about in his presentation. And this is how we're working towards building these really incredible devices that I think you guys will get, hopefully, after the first shipment on Thursday. So this is our provisioning stage. So this is what happens after flashing, and we do that initial check. We make sure there's nothing obviously wrong, like does it have all the sensors or is it missing the modem? After it passes those basic checks, it goes on to final provisioning. And these are some very early comma 3s. And we started writing these tests fairly early on. We wrote these tests a couple months ago, and we've really iterated on them in the last couple of weeks. But these are some old revisions of the comma 3. And they, you can see some of them failed, some of them are still running the test, and some of them passed, but it's cut off. And we verify things like sensors. Is Wi-Fi working? Is LTE working? Are all the things the right firmware versions that we expect? Is the camera in focus? This is becoming more important with the comma 3 because we focus the cameras ourselves. We have a lot of control over the process, but this means there's a lot more that can go wrong. So testing becomes a little bit more important in some aspects of the comma 3. Then we also do some testing with the panda, the internal panda, so the Uno and Dos in your comma 2s and 3s. And we can basically be confident about all the hardware that we're shipping out just based off this quick test. This test runs in a couple minutes, and it asserts all the instantaneous functionality we can check. We do some, there's in the daughter board that George talked about in his presentation that goes on top of that modem on the comma 3. There's a beeper, and that fires when device powers off, essentially, while it's still engaged. And we do tests like that. You hear these all throughout the office. We go through a lot to test these devices. We have some really cool tests with that. And then it also does the server registration. And then we do the stress test. So this one's pretty cool because we have all sorts of different failures we caught on the stress test. We check for temperature. This one used to be super important in the comma 2 because the device would fail a lot. We check for GPS accuracy now. We do a lot of camera checks, like are we dropping frames? Are we getting any errors from the camera at all? This indicates some kind of assembly defect where a screw isn't screwed in all the way, stuff like this. And we have these very strict checks. And it runs for continuous 24 hours. No, like, if it happens 2 times, we'll let it pass. These are super strict tests. It turns red when it fails. It's alarming. We pull it off the rig, and it goes back in the production process. And then this is a pretty cool chart. So we ship the comma 2s with some testing that we could think of beforehand, but there was a lot of unexpected failures with them, and a lot of the tests were written after things happened in the field, and then we found out that this is something we really need to test for. This is something that varies quite a bit from device to device as we still establish these production processes. So this, this kind of shows how we improve these devices over time and how every device that has been shipped also benefits from the improvements from the devices that we make in the future. So we used to set aside all the Comet 2s that failed. This is our first serious time doing production, so we'd do the tests, and if it failed either final provisioning or the stress test, we put it to the side, and it goes in a bin, and we just have walls and walls of particular failures, ranging from very minor things like we need to fix up some solder joints or something, to the CPU's too hot, this is some kind of device failure, or we need to do something more major to fix this. So CPU too hot around, I think, September, October of last year was by far the biggest and most common failure for the Comet 2s. So we reduced CPU usage in openpilot, and then we downclocked the CPU fairly significantly to get these devices to pass the stress test. And we went a little bit above and beyond here. We did a more extreme downclock, and the orange part of the histogram here is the devices that were too hot and failed the stress test after the downclock. And the blue ones are all the devices we shipped before that with the current clock frequency. So the devices that were too hot actually ended up being running even cooler than devices we shipped out before that passed the test. And then every device in that blue category also benefited from this because we shipped an OTA update to the kernel, and all the devices got cooler in the field. And then this is pretty cool. Here's a GIF of the screen calibration. So we've thought about Comet 3 testing for a long time and how we're going to test them in production. And we got to do some fun stuff before we shipped out the first units. So I think this kind of shows how far we've come from the Comet 2 a couple years ago to where we are at with the 3 right now, where we can do things like this. And you look at them, and the stress test is, we go back to stress test. The stress test is pretty big. This is a small part of it. And you can see all these devices on the stress test, and their screens look exactly the same. This is, we put a Comet 2 next to the Comet 3s yesterday. And the difference is incredible. These devices are really beautiful. And we have time to do things like this now in the capacity. So I think you guys will be really happy with these devices. And then now we're going to take a trip to the Comet Zoo. Well, to the premier San Diego Zoo, which is Comet Zoo. And we're going to talk about the Panda Jungle. So the Panda Jungle is what most of us who have a device on our desk use to do replays and to debug and develop openpilot. So Panda Jungle essentially has a Panda on it, and it has 6 OBDC ports. So you can plug in 6 Comet 2, 6 Comet 3, 6 Pandas, whatever you want. And this is how we do our hardware-in-the-loop testing for Pandas. This is how we develop openpilot on desks. You can essentially emulate being in a car on your desk. And it's an incredible debugging tool. And then now it has a working ignition button. We shipped 9 of these devices in the since we started selling them. We shipped 9 of them. And we just got the ignition button working. But we have an announcement. It's going to be $199 now. All right. So hopefully we'll get another 9 people to buy them. And we have the next-gen Panda, red Panda. So the red Panda is based on an STM32H7. The previous generation of Panda was based on the STM32F4. We've been doing work in the last 3 months to develop this device and bring it up. It's the future of the Panda platform. It supports CAN-FD, has a 4x faster CPU, and it's red. So it's the same Black Panda form factor in a red case without GPS. You'll be able to connect this to your Comet 3 directly into that USB-C port. And then you can buy one today, $299, and it ships in 2 to 8 weeks. And we're optimistic we'll have support in openpilot in the next release, 088. All right. Questions?
Hi, my question is about testing.
Yeah.
So you did a great job describing the system level post-production tests with the test closet. It sounds like when you have failures, the devices go into a rework process, and that's expensive not only from a time standpoint, but others as well. I imagine you'll be selling hundreds of thousands of these devices. Can you talk about the testing that goes on during production so that reworks don't need to happen to increase your yield?
Okay, so there's a couple things there. We're not quite at the scale of selling hundreds of thousands. Yeah. Yeah, maybe. But as far as reworking the devices, it costs a lot of time. But it's really clear now that this time is really worth spending. It made every Comma 2 we ever shipped out much more reliable and a much better product. So I think right now the time we invested in, and we do this kind of in stages. So we do the production process, we build devices, we set them aside, and then it's kind of like the find interesting loop. We look at the top failures, we fix them, or we evaluate what can we do about these. Can we improve processes? Can we improve the software at all? Like, where can we do better? And it turned out for the Comma 2, we fixed all the common failures, and this made all the devices that much better. You buy a Comma 2 today, and it's incredibly well tested. So yeah, it is worth spending the time, but we do it in stages. We don't just immediately rework them. Was there another component to your question? I think I covered everything.
I guess since you asked, yeah, I don't. Oh, no thanks. Yeah, the question wasn't to say rework isn't worth the time. It has to happen if the test fails. What I'm saying is,
How can we catch them earlier?
were the tests upstream during production that would just prevent reworks from ever needing to happen, like catching the module level failure before it gets assembled into the device, and then the stress test is the area that it's caught.
Yeah. So we try to push tests downstream as much as possible into the earliest stages, and we've gotten really good at this with the Comma 3s already. Actually, we catch almost all the failures in final provisioning, which takes a couple minutes. You build the device, you flash it. There's a couple stages of flashing actually. So we flash just the boards themselves, then we build it into a device, then we put Agnos on it, and then we do some final provisioning. And we've gotten really good at this actually. So we add these tests when necessary, and yeah, the final provisioning tests are really quick, where we catch these super early in the production process actually.
We have another one up here actually.
Oh, yeah, thanks. Thanks again. Nice presentation, nice work on testing. One question I have for you guys, maybe like for improvement. Are you guys planning on doing like some thermal cycling of the devices?
Some thermal what?
Cycling, like freezing them basically like to -10 or -20 and then heating them up pretty quickly, because that's what really happens in practice. And my device actually had a problem, Comma 2. After we slowed trip, when it stayed outside and cooled down to -10, screen just stopped working.
Okay. So I think your question about thermals, I couldn't quite understand.
Yeah,
the
like
last part of
thermal testing. Like, do you guys plan on doing like thermal cycling?
Yeah.
Of new
So
devices?
I think we plan to we cover all the hardware right now pretty thoroughly, but there's a lot of room. There's a lot of depth to go into in the testing. And our testing will get much better. We'll go through the same process we did with the Comma 2. The Comma 3 testing is where the Comma 2 testing it kind of picked up from there. We didn't start over. So I think the Comma 3 testing will be really, I think it's quite incredible right now. I think it's going to get, you saw the screen calibration.
Yeah.
This is.
But then what I'm saying is that Comma is not really, is a little bit different from consumer electronics, because its operating condition can go from -10, for example, Celsius to I don't know, 80 degrees pretty quickly.
Yeah.
So that's not your PlayStation like use case scenario usually.
Yeah. Yeah.
Yeah, just something for improve. Thanks.
So with the red panda,
Yeah.
in the new car or in the comma car configurator, when you're trying to see if your car is supported, if you need a red panda to support your car, is that going to show up in the configurator?
Yeah, so this is something we could easily do. No cars require the red panda right now, but I think some cars are starting to ship, like some Genesis cars are starting to ship with CanFD. When the first CanFD carport comes in, we'll handle this all nicely.
Gotcha. And can you maybe speak to what's on CanFD and why it's important to have that support in the red panda?
Yeah, so it's just an upcoming standard. It's kind of the next step in CAN. The FD stands for flexible data rate. You can get more data through faster. So this is what the cars are going to be shipping with. We want to support it. It's also just changing one chip. So this is pretty cool.
We have one up here again.
I'm sure another question on the red panda. Since there's a panda in the C2 or the C3 already, how does that work? Do you bypass one? Do you switch one off? How does?
So you won't be able to use it with the Comma 2, unfortunately. This is a hardware limitation to Comma 2. It's the same reason you can't use a Comma Smaze on a Comma 2.
Okay.
So I guess if you have an Eon, you can use the red panda, but an Eon Gold.
So
But it'll use the USB-C port on the Comma 3.
oh, the spare one. Okay. Okay.
Yeah,
Cool.
we have one of our cars. We have a red panda in one of our cars driving with a Comma 3.
Okay. Cool. Thank you.
So one of the things you listed was MISRA C2012. Is that being applied to the Panda and also the openpilot?
No, so openpilot is considered QM in terms of our functional safety analysis. Panda is where that kind of code rigor happens. And this is where we designate the safety being enforced.
Okay, and are you applying anything like then CERT at all to the, for security, another coding standard? Considering, making sure that the code is written a certain way so there's no vulnerabilities or anything like that. MISRA does that in some sense, but wondering if there was any other standards that you're applying.
MISRA, you mean as far as coding standards
Yes,
or as
coding
functional safety? Okay.
Coding standards.
So on the C code, we just run some generic static analysis tools like CPP check. So we use CPP check, we use some of their static analysis stuff, and then they have a MISRA add-on. And then we keep up to date with their MISRA add-on. We fix a couple bugs in there. So we pretty actively work towards MISRA C 2012.
And for functional safety standards, are you then applying like ISO 26262 process standards for?
Yeah, so you can see, it's pretty cool. If you go to Panda, you'll see we have two projects. We have an ISO 262 project and we have a SIL2 project from when we did our in-depth functional safety analysis. And we made a bunch of issues, and then you can see the progress. All the ISO 262 stuff is almost done. All the cars that we officially support have full ISO 262 in Panda.
And you self-certify as well the code or for safety standards, like?
Yeah, there's no certifying body.
There's no, okay.
You said something about declocking one of the chips to reduce the heat
Yeah.
in Comma 2. Are all the Comma 2s that are out right now with the declocked?
Yep.
Okay, thanks.
Yep, and running at about 55, 60% overall CPU. So this is well below our target for 09, openpilot 09.
Thanks for the presentation. So the one question I have is, what will be the operating temperature for the Comma 3? Will it have the same limitations that the Comma 2 has, as far as maximum temperature that it can be run at?
So the active cooling in the Comma 3 is quite a bit better. The thermal thresholds may be a little bit stricter because from what we've seen on our stress test, thermals are significantly better. We see about max temperature of 65 C. You'll never see a Comma 2 with 65 C. And this is the max for the Comma 3. we might be a little bit more strict, but it's because we have more room to be strict, and you'll see the active cooling is quite good in the COM 3.
Hey, how's it going? I'm curious what yield you guys tend to get on the production units, and when production units fail quality control, what tends to be the sort of common culprits?
Yeah, so like I said, we do it in stages. So we kind of establish processes, we write tests, and then production comes back after some period of time, a couple months or so, and they're like, okay, here's what failed a lot. We have a lot of logging around this. That's why we're able to make these cool histograms and stuff, comparing like all the Comet 2s we shipped up until now, and then compare with the down clock. So some of the common ones we saw with the Comet 2 were like CPU too hot. Some of them don't have an IMEI. So we're able to filter out a lot of the raw eco phones. There was tons of failures in those. That's like kind of a cost we just have to eat. So we do a lot of filtering at every level, and each kind of stage had its own common failures. Stress test was CPU too hot mostly. Final provisioning usually catches things like, oh, this device doesn't have a microphone, stuff like that.
All right, Adeeb. Thank you so much. That was great.